Hello. Hello and welcome to this video where we will continue the read through of permutation and combinations. We have done till this permutation with repetitions. Now we will do with combinations with repetitions. So my recommendation is that you do not watch the video first. You go and read the PDF. The link is in the description. Read sections yourself. And if you don't understand anything, ask me questions. Because I doubt there will be anything extra I'll be explaining other than what is written. Okay, I'll be mostly reading it through. I don't expect you to watch the video for the understanding. If you like to listen, you are most welcome. Okay, some people don't want to read; they want to listen. So if you want to listen, very well. Then we get started. So the first topic is combination with repetitions. Now, there are roughly 10 pages remaining, so I'll try to finish it by tomorrow. This video and one more video, and we'll try to finish the theory. The objective is to find combinations of R objects out of N objects under different cases of repetitions. To begin with, we consider combinations of R objects taken out of N objects, of which P are of one type, Q of the second type, and so on. Let the different things be denoted by the letters AB. Now we consider the product 1 plus x plus a square x square through a to the power x to the power p. This should be p. And then 1 plus bx plus b square x square through bq to the power q. This should be q. So two typing mistakes already. All the terms in the product is of the same degree in the letters a, b as in x. The coefficient of r, x to the power r, is the product. In the product is the number of ways of taking r of the letters a, b with the restriction that maximum number of a's is p, maximum number of b's is q, and so on. Quotient of xr will not, x to the power r will not change if a is equal to b is equal to so on is equal to 1. Thus required number of combinations is quotient of x to the power r in 1 plus x square up through, this should be x to the power p, and similarly x to the power q, and so on. Similarly, number of combinations of R objects out of N objects, of which N are of one type, Q are of second type, and N minus PQ things are all different, will be given by quotient of x to the power R in 1 plus x square, and so on till x to the power p, multiplied by 1 plus x square through x to the power q through, multiplied by 1 plus x multiplied by 1 plus x to n minus p minus q factors. So what we are looking for is quotient of x to the power r in 1 plus x square through x to the power p multiplied by 1 plus x squared plus x to the power q multiplied with 1 plus x to the power n minus p minus q. This 1 plus x is extra, it should be removed. Similarly, number of combinations of R objects taken out of N, of which P are of one type, Q are of second type, and so on, when each thing is taken at least once, is equal to quotient of x to the power Rn x plus x square. Notice 1 has been removed here, and so on. And it will be quotient of x to the power r minus 3n 1 plus x square through x to the power p 1 plus x square through x to the power q. If n is a negative integer, then 1 plus x to the power n is equal to 1 plus nx by 1 factorial plus n into n minus 1 by 2 factorial plus x square. So this comes from binomial theorem. So some part of this chapter is dependent on binomial theorem. If you don't understand, please wait for binomial theorem to be finished, which should be next to next chapter. I believe next chapter is induction, mathematical induction, and then we will study what is called polynomials. So if n is a positive integer, then 1 plus x to the power minus n is the same formula. coefficient of x to the power r in 1 minus x to the power minus n is n plus r minus 1 CR, which is the number of ways in which r identical objects can be distributed among n persons can get 0 and more objects. The coefficient of xr in this equation is 1 plus x to the power r plus 1 by 1 minus x whole to the power n, which is equal to 1 minus x to the power r plus 1 into 1 minus x to the power minus n. So this coefficient is equal to n plus r minus 1 CR. Now we have something called integral solutions of equations. So suppose we have r x values x1, x2 through xr is equal to n. Now we want to distribute r identical object among n persons where each person gets 0 or more things. That is equal to n plus r minus 1 CR. Similarly, number of non-negative integral solutions of equation x plus 2y plus 3z plus 4w is equal to n will be given by coefficient of x to the power n is 1 minus x to the power minus 1, 1 minus x to the power minus 2, 1 minus x to the power minus 3, and 1 minus x to the power minus 4. Similarly, number of positive integral solution of the equation, the same equation, is equal to coefficient of x to the power n minus 1 plus 2 plus 3 plus 4 in this expansion. So it is said. So the difference is here, these numbers x, y, z, w can be 0. Here they cannot be 0. That is the only difference. So the coefficient difference comes from that only. This bracket is not at appropriate place. Now some geometric applications of combinations are given here, which if you want, you can go ahead and prove it. And non-concurrent and non-parallel straight lines are there, then point of intersections are NC2. The number of straight lines constructed out of 8 points when no 3 points are collinear is NC2. Given n points, if m are collinear, the number of straight lines possible are NC2 minus MC2 plus 1. In a polygon, number of diagonals out of n points when no 3 points are collinear are n into n minus 3 by 2. So these are easy, you should try to solve these, okay? I'm not going to explain it, but if you want, let me know in the comments, I'll explain it. You'll see the usage of these when we solve the problems. So while solving the problem, I'll explain it. For now, I'm not explaining it because I expect you to figure it out yourself. These are very simple statements. Number of triangles formed from n points when no 3 points are collinear are NC3. Number of triangles formed out of n points in which m are collinear is NC3 minus MC3. Number of triangles constructed out of n points when none of the side is common with the sides of polygon are NC3 minus NC1 into n minus 4 C1. Number of parallelogram constructed by two system of parallel lines where first set contains m parallel lines and second set contains n parallel lines are NC2 into MC2. Number of squares formed by two system of parallel lines in which first set is perpendicular to the second set of lines when first set contains m parallel lines and second set contains n parallel lines is r to the power sum of m minus r into n minus r, where r varies from 1 to m minus 1 and also m is less than 1 n. Now we have number of divisors and sum of divisors. So suppose n is equal to p1 to the power n1, p2 to the power n2 through, this should be k, pk to the power nk, where p1, p2, pk are distinct primes and n1, n2, nk are in the set of positive numbers. Obviously, any divisor of n is of the form d is equal to p1, m1, p2, m2, pk, mk, where m1, m2 all belong to natural numbers, such that 0 less than equal to mi less than equal to ni. Now I is equal to 1 through k. Therefore, total number of divisors of n will be equal to number of ways of selecting at least one from n1 identical prime numbers p1, n2 prime numbers p2, and so on. The number of such ways is n1 plus 1 into n2 plus 1 through n1 nk plus 1. This divisor will also include 1 and n, so obviously number of divisors other than 1 and n is n1 plus 1 into n2 plus 1 in through nk plus 1 minus 2. The sum of all divisors for n is given by sigma r1 is equal to 0 through n1, sigma r2 is equal to 0 through n2, and so on till sigma rk is equal to 0 to power, rk is equal to 0 to nk, p1 to the power r1, p2 to the power r2 through pk to the power rk. Now, if you sum this, it will be equal to p1 to the power n1 plus 1 minus 1 by p1 minus 1. P2, this is geometric progression, we can figure out it from geometric progression. P2 to the power n2 plus 1 minus 1 by p2 minus 1 and so on. Now we have something called exponent of prime p in n factorial. Let EP of m denote the exponent of prime p in the positive integer m. We have EP n factorial is equal to EP 1.2.3 and so on through n. The last integer among 1, 2, 3 and minus 1, n, which is divisible by p, is n by p into p, where this is the integral function where x inside brackets denotes the greatest integer less than or equal to x. So EP n factorial is equal to EP p dot 2p dot 3p through np by p, and that is the integral side of it. Because the remaining integers from the set 1 to 3 through n minus 1 and n are not divisible by p, because p is a prime. So that, if we have to calculate, that number is equal to integral part of n by p plus ep 1.2.3 through integral part of n by p. The last integer among 1 to 3 to integral part of n by p, which is not divisible by p, is, so we compute this, is equal to n by p square p. So then n by p square comes out and it becomes n by p square. So you continue this and you get EP n factorial is equal to integral part of n by p plus integral part of n by p square and so on till n by p to the power s, where p to the power s less than equal to n less than equal to p to the power s plus 1. Now we have a very important principle called inclusion-exclusion principle. It's a long one, so I don't know if I should start this in this video. No, we will study inclusion-exclusion principle and everything in the next video. So what we are remaining with is, we have 6-7 pages, but we will study this in next video. We are at page number 157 and we have to go till 163. Okay, so 163 is quite empty, right? So we will study this 5-6 pages in tomorrow's video, and we will finish this entirely, the theory part of it. Okay, I don't want to start inclusion exclusion principle and derangements, because those are entirely different kind of they require different kind of thinking, they require a fresh mind. So go ahead and revise all what I have taught. Okay, if you find any mistakes, let me know in comments. There are some typing mistakes as we saw. It's here, then we have here, 4 mistakes, and there were further mistakes as well. This bracket. Okay, so I'll end this video here, and I expect you to go through all the theory, because once the problem starts, there will be no explanation of theory. You need to know the formulas. If you don't know the formulas, you will get stuck, right? So make sure you have good grasp on theory, and more importantly, not only you understand, but you also remember. Okay, remembering is important. Otherwise, all the time you'll have to refer back to formula. What are the formulas of this and all that? So I hope that you are finding these videos useful and informative. So let's meet tomorrow around at the same time, 1 or 2 p.m. India time, and we finish the theory part of permutation combination. Thanks a lot for watching the video. I'll see you in the next one. Sayonara.